Okay, this is how to solve radiometric dating problems. So radiometric dating is the process of using radioactive isotopes to determine the exact age of a rock layer. And so we did this using half-lives in our Skittles lab. So radioactive atoms were our S up that we put back in the cup. And the stable or daughter atoms were what we put S side down in the pile to eat. And so the difference in a real rock is that those atoms would stay inside that rock. So just like in our sample, it would start off with all radioactive isotopes, except for this white area is like the other minerals that would be in the rock. So if we counted up those U's, there's 32. And then after one half-life, we dumped them out. Some landed S down. Those were the pile we could eat. They would stay in the rock. In order to make our model work right, we had to move them off to the side, but those lead atoms would still be there. So if we counted up all the atoms, we would still see 32 atoms, but now 16 of them are lead. Half of them, that would be about 50%, and that would be one half-life. And so that half-life is the important part. It takes an amount of time for that to happen. So in this case, it's 1 billion years old. So we dumped that next round of 16 Skittles back out, and half of them flipped over again. So now we see that there's only 8 parent atoms left. The rest are all in the pile we could eat. So that makes about 3/4 of those at that point, or 75%, are already decayed. And that continues on until you're left with all the daughter atoms. And so we can use this process to figure out how old something is. So you're going to see some different kinds of problems. So the first step is to figure out the kind of problem that you're dealing with. You're going to see percentages, fractions, or quantities. So here you see I have these color-coded. You're also going to see it talked about in terms of the radioactive or parent isotope and the stable daughter isotope. So if we look at this first sample problem, it's easy. We can see the first two, we can see that there are percentage signs. So we know those are percentage problems. This first one, we have to be careful when we read, though, because it says radioactive atoms, so that makes me think it's going to be parent. But if it says to decay, that actually means stable daughter. So you'll notice that I have color-coded that and marked it as stable daughter because it has that word to decay. So another way they could say that is just by saying daughter atoms. A fraction, also going to be easy to identify because I'll see that fraction symbol, and then sometimes it'll say parent, sometimes it'll say radioactive, whatever. The last kind of problem is going to be a quantity problem, and you might see this, there's a couple ways. It might talk about a ratio. It might actually say the word quantity, so it might say how much or how many. If it says ratio, it might talk about both parent to daughter isotopes. So this is talking about both the parent and the daughter, and it's represented by this ratio right here. And so we can see this is parent, this is daughter. Another way you can identify quantity problems is they might use numbers like this. So this one's using an actual number. It might have values like grams, kilograms, or milligrams. Oops, that was for me. And so then what we did was we see that we have to figure out how many half-lives it takes for a certain amount to decay. So percentage problems, we're always going to use this percentage t-chart. Fraction problems, we're going to use a fraction t-chart. And quantity problems, we're always going to use a quantity t-chart. They always start the same way. 100%, the whole fraction or the total always goes above the t-chart, and 0 also always goes above this side. We'll always put the parent on the left, and we'll always keep track of the daughter on the right. Okay, so you always set up a t-chart the same. The thing is we'll know always about half of those atoms flip over. So half of 100 is 50. The other 100%, I'm keeping track of all 100% the whole time, right? So then half of 50 is 25, but I'm keeping track of all 100%. Half of 25 is 12.5, but I'm keeping track of all 100%. The same thing works in a fraction. Half of 1 is a half, so I just am keeping track of that whole fraction. So I like fractions. They're pretty easy because I know what half of a half is. That's a fourth. I put the rest of the fraction on that side. My math is pretty easy. And we're not going to show an example of a quantity problem yet because those we have to build each and every time because those are going to be different starting values up here. So let's try it on this first one. This one says how many half-lives will it take for 75%, so that's the number I'm going to match, Radioactive atoms to decay, that's this side. So I look to find the match for 75%, and I see that right here. So I got that from this. So I know it was 2 half-lives. So this is the number I'm finding. That tells me this half-life number right here. If I did the next one, 87.5, again, that means 3 half-lives. So I see the match on the daughter side, and that tells me I have 3 half-lives. If I do the fraction one, 1/16 of parent atoms tells me I'm looking on this side. I'm looking for that number 1/16, and I see that right here. So I know it was 4 half-lives. So 4 half-lives goes right here. So let's do this quantity one. So what I did was I grabbed this image with my select tool up there, and I pasted it right down here, okay? And so when it's talking about a ratio of parent to daughter isotopes, it's giving me each piece. So in order to fill out my T-chart, I have to know the total. So I took 875 plus 125 to get 1,000. 1,000 is what goes up here. So I start with the total. Then all I do is I do like I did up here. I divide by 2 my way down the parent side. So 1,000 divided by 2 is 500, but I'm always keeping track of that total. So then half of 500 is 250. I'm always keeping track of that total. Half of 250 is 125. Notice how that number matches. So just like before, those numbers match, so I know it was 3 half-lives. Now there's an alternative way to do these quantity problems. If that feels intimidating, it feels like it's going to be a lot to do all those divided by 2s, I could also change it into a percentage. So I could take this parent isotope, and I always do parent because it's easier. You just have to rip down the left-hand side. You don't have to worry about if your math is right over here. So 125 divided by 1,000, if I multiply by that by 100, I get 12.5%. 12.5% is still 3 half-lives. So then the next step is to multiply. Each one of those half-lives takes an amount of time. So it might take 1 billion years, it might take 10 seconds, but each half-life counts as an amount of time. So you'll be given the amount of time. So if you know it's 2 half-lives, you just take 2 times the amount of time, and that tells you how old it is. So if it's 4 half-lives and this is the amount of time, 4 times 5,730, it's your number of half-lives. So that's the steps to the problem. So let's go ahead and try one. The half-life of potassium-40 is 1.3 billion years. We're always going to give you that. A sample is found and has 3.12%. All I have to do is come up here, grab my percentage T-chart, and it stops at 12.5. So what that tells me is I'm going to have to do a little bit more work. So you see I pasted it there, and I'm looking for 3.12 parent. So I took that 12.5 and I divided it by 2 to get 6.25. I divided it by 2 again to get 3.12. 3.12 is the number I was looking for here. So I know it was 5 half-lives. Now, I'm not done because it's asked me how old the sample is. So now I have to take that 5 half-lives times the amount of time right here. So 5 times 1.3 equals 6.5 billion years old. The next one is a ratio, so I know it's a quantity problem. So I'm going to grab that quantity T-chart, this empty one right here. I'm going to drop it down here in the bottom. And as I drop it, I'm going to look for the total. So 125 plus 1875 gives me 2,000. So I started with 2,000 up here. And then I started dividing by 2 until I got to 125. So 1,000 is half of 2,000. Half of 1,000 is 500. Divide that by 2 to get 250. Divide that by 2 to get 125. That's the number I was looking for. And if I'm feeling efficient, I might not want to do this section. But what I would do is then figure out, what do I know that this equals the rest? So I would take 2,000 minus 125. Did I get 1875? Does that match over here? So you could double check your work that way. Well, that number gives me 4 half-lives. So I take that 4 half-lives times the given 1.3 billion years equals 5.2 billion years old. Now this is one of those times I did not give you real data. Okay, we made this up. The next one is also a quantity problem. Notice that G right there. And it says aluminium decays into bergmanium with a half-life of 25 years. So this one's obviously made up data because there's no elements named after us. It says how much aluminium would remain after 4 half-lives. So this time I know I'm going to do this process 4 times, so I went ahead and just numbered that. And then I took that 400 total that it told me it started with, and I started dividing by 2. So here's when you can tell I just didn't do this middle section because I got efficient. I won't say lazy, I'll say efficient. So 400 divided by 2 is 200, divided by 2 is 100, 50, and 25. So I know it's 25 grams of aluminium, and it's asking me also about the bergmanium. So I know that 25 plus the amount of bergmanium should equal 400, because 2 plus 2 equals 400, and 1 plus 300 equals 400, and 50 plus 350 equals 400, and 25 plus 375 equals 400. So we're always keeping track of that 400 total. We know where all of those grams went because matter cannot be created or destroyed. So we know that the amount of bergmanium is 375 grams in that quantity problem. And then finally, we have another quantity problem that's a ratio. And this one I did 2 ways. So on this one, there's our ratio that we were given, and the grams is what told us it was a quantity problem. So we add those together to get 500 grams. That's how I knew what total. And I could either take this and make it into a percentage and do it as a percentage problem, or I could take that and divide my way by 2 until I got to 15.6 grams. No matter which way you do it, notice that you get the same amount of half-lives. You get 5 half-lives. So 5 half-lives times 25 years equals 125 years old. So those are samples of all the